Thanks for starting the recording, Michael. Again, if you didn't hear that, we are recording this part of the event. Just as a recap, this is what we call the FGF, or Fused Granular Fabrication User Group. It's our attempt to try and help support good dialogue within the community and lesson sharing, as FGF is such a new and evolving 3D printing domain. And just in case you didn't hear this before, we do sell an FGF 3D printer. My name is Samantha. I am the catalyst for ReCreateIt, a large format 3D printing company. But know that this is our effort of supporting the community, regardless of if you have our platform or if you've worked with us. So if you see RE3D, we're connected to the same company. We'll be hosting this recording on our RE3D printing. We'll put a link in there. YouTube channel if you want to go back and listen to it later or listen to past ones. We did attempt to start these about a year ago. If you had seen any of the videos or if you were part of it, the scenery changed every day because we were in the process of moving. And then it just became too ambitious for us to support every month. But we're going to go ahead and take a crack at making these regular. If you have feedback about the time or the format, let us know. To date, what the community has appreciated is allowing someone to present on what they're learning in FGF. That could be you. Providing time for Q&A. Once it kind of gets to a lull in questions, we'll turn the recording off in case you want to ask one that's not recorded. And then just open networking and lesson sharing. At the end, we'll see if anyone wants to present at the next one. Typically, the talks, if you're interested in presenting, are anywhere from 20 to 40 minutes, we find is a good mix, just to allow for questions and answers. But we so appreciate everyone that dials in from around the world. We look forward to getting to know you. If you want to share your company or your project or your LinkedIn, feel free to put that in chat. But with that being said, we'll go ahead and get started. So today I have the pleasure of introducing our teammate, Dr. Amber Douglas, that works at ReCreateIt. She has a significant amount of experience in polymers, which is great for us as we do polymer FGF. And she has a PhD in material science, engineering, and commercialization from Texas State University, San Marcos. And her research, she focused on synthesis and characterization of novel polymers and nanomaterials with a focus on commercialization. So Amber's been a great gain for us. We were able to bring her on as a result of ReCreateIt's research with the National Science Foundation, Habitat for Humanity, Restore Austin, University of Texas, Georgia Tech, University of Wollongong, and Western Sydney University. We call that effort ReCreateIt. We can throw a link here in chat, but Amber's been instrumental in helping us as the prime look at working with some of the hardest waste materials to 3D print directly from shredded up reclaimed plastic. So with that being said, she offered to share some of our experience working with polyolefins, which previously we were told was going to be really difficult to do without a blend. And she's made a lot of progress and is helping us with characterization. So she offered to share her perspective on that today. I hope you find it helpful, and we look forward to the questions. I'll turn it over to you, Amber, and turn off the dog.
Thank you, Samantha. Thanks for introducing me. So I guess this is going to be, I'll say about half kind of some background on polyolefins, the semicrystalline nature of them, some of the challenges that brings to the table when you're printing with it. So here's a table of contents that we're going to look at. And some of the order has changed because it's kind of a 2-day put together presentation, but I would like to cover most of what's in here, some defining what polyolefins are in the first place, what crystallinity really is, and how it can be a challenge and how you can dial into that and play with it. And we're still learning how to do that right now. And then maybe some previous work in additive manufacturing. I didn't include many examples because there's not too many right now. I mean, there is some, there's not many with, with functional parts or with pictures or anything like that. So I kind of talked through it a little bit. And then working with crystallinity, and that's kind of what the game is here with that. We talk about it, and then we set our prep parameters. I'd like to say I'm working with Chris. He's here probably, I think. Is he here, Samantha? But he might be on the
Chris is actually in the process right now of wiring up the granulator for our Gigalab at the Restore.
yeah, I figure he might still be there. But so I work with a gentleman named Chris. Chris is helping me with this, and we have similar prep parameters, but there's some differences. So if you ever have any questions, we can both provide input if you need to at some point. And then, like Samantha mentioned, we're working with NSF grant, a convergence grant, and it's ReCreateIt talk about some of the successes we've had there. And then some of the ongoing work we're going to continue to do with polyolefins. Yeah, the next step. So really, it all boils down to structure-property relationship. You know, you learn a lot from other manufacturing techniques too. So I'll go into some injection molding stuff here in a minute. But polymers in general are polymers made from oil-based products or natural gases, but really they're just a double bond. You have a double carbon-carbon bond, and it's just an alkene molecule, and they polymerize that. So that can make a wide variety of polymers. What we really look at is HDP, LDP, PP. They mentioned PB in some literature, but I haven't seen much of that or heard much of that as an exciting new material or anything. But they can make linear or cyclical polymers out of them. Most of them, almost all of them, are semicrystalline. So they're going to be a challenge when it comes to printing because they're going to all have the same issues. Let's see. Okay. Don't know why I doubled up there. So like, and I know probably most of you know what these are, but amorphous polymers are going to be very different from semicrystalline polymers. Well, structure-wise, they're not going to have any organization really between between each polymer chain. They're going to kind of look like a spaghetti bowl of noodles that are not. I mean, they're not liking each other, but they're not associated with each other in any sort of electrical way, any sort of ionization way. I mean, in any sort of mechanical way. They have poor chemical resistance. They pick up moisture pretty quickly, and they lose dimensional stability over time. Whereas semicrystalline polymers, they have really good mechanical properties and really good, and that's to do with that crystalline bond that they're having there. So it takes a lot of that. So because of that, to break that down, you would have to have really strong chemicals to be able to dissolve any sort of crystalline polymer. And even still, you have to have really high temperatures when you're putting a solvent in that to dissolve it. So it's really good with chemicals. It's hydrophobic for the most part, unless they add some sort of functionality to it that increases its hydrophilicity. And for the most part, they're pretty rigid and they're pretty inflexible, unless you add some sort of flexible additive in there to space out the crystalline structure. So a little bit more about that though. So you see that crystalline polymers are different from amorphous polymers in that they have both. So you have crystalline regions and then you have these amorphous regions. And so you have a TG, you have a TM, and you have, a crystallinity point as well. So when it goes through the TG, now the material can move, but you're not seeing it move, right? It's just solid. But it is moving and it's forming, depending upon the temperature you have it set at, it's going to continue to form crystalline associations with the nearest polymer it can find. Or itself, it kind of curls on itself too to make a lamellae structure. But so it goes through a TG. So like I said, you don't see that. So that can affect your bed temperature, for example. If you have your bed temperature really high, but it's still not melted, you could be forming really strong crystalline associations right there, and then it could pop off the bed at some point because they get to a critical point and just get too strong to stay there. But it also has a melting point. So that is different than, because when with the amorphous polymer, you only really have the TG, and then that pretty much is the rubbery polymer after that, and it gets softer and softer and softer until it becomes a liquid and eventually decomposes with increasing heat. So what you see with crystalline polymers that you don't see with amorphous polymers, though, is this big jump in volume. So the shrink rate is quite a bit more than you'd ever see with an amorphous polymer. You can see that in that diagram right there, the first order crystallinity. Crystallinity affects everything about the polymer, the mechanical properties, the thermal properties. You see here, the best polymers for any sort of mechanical, and I just included elongation at break for as one example, but it outshines almost every polymer, including some of these peak and everything in here for elongation. So it's really important if you can work with it, you can make a lot of money off it. You can design things that you cannot do with amorphous polymers. Okay. So this is basically a diagram of the amorphous region would be in between these lamellae right here. The lamellae is when they kind of associate with their own self and they fold it around, and then there's some of the amorphous part coming out. Polyethylene and polypropylene can have up to about 70% crystallinity sometimes. So that region can be pretty small, and you'd have a lot of those little sphere lights right here. So if you're looking at it in a microscope, you would see just a bunch of those little circles right there. And you wouldn't know that if you zoomed in there, you'd see some amorphous in there too. But if you imagine trying to, you know, break that or pull that apart and do elongation, it's going to act like a cross link almost. It really is not going to, it's not going to break as easy as amorphous. So this is, I included this because this is how your process can affect your, and they show different, you know, different parameters that they've set things to. For example, they have fast cooling rate, slow cooling rate down here. And it just, almost anything that you do with temperature or rate of anything is going to increase or decrease your crystallinity. And you want to think about that ahead of time, probably. Let's see. Okay. So this is something I've been studying lately because I have an interest in this. We've been able to successfully print here at ReCreateIt pretty nice parts, but if to really get it consistent and to have it to really own this type of printing, you would really need to understand the alpha, beta, and gamma crystalline phases that it has. And a lot of people, if you buy a filament, for example, it's going to have some sort of beta nucleating agent in there. Beta nucleating agents are just a different type of crystal structure than the primary one that's more thermodynamically stable. If you print with neat polypropylene and you get a print, it's almost always going to be alpha. But if you want beta has larger crystals, they take a lot longer to form, and so they decrease the time. I mean, they give you more time to print with, basically, before it pops up or starts curling up at the edges. Let's see. And I think mostly what I started studying and what Chris looked at as well was the injection molding. And what they pretty much exclusively say, you can pull up 20 papers and they all say the same thing, is to control the mold temperature and the extrusion temperature and just decrease it. The lower, the better. If obviously you want to have some flow. They have the benefit of having pressure because they, you know, push it. But we don't. So we have the extrusion temperature that's coming out. We can control the temperatures, but the lowest you can get it without it getting too hard, the better. Then the mold, for us, that wouldn't be the mold, right? It would be the bed. But if you have it too high, you have crystals that are forming, you just can't see it happening. And it still may stay clear and you still don't even know that it's happening. And then all of a sudden you look at it wrong or you breathe on it and it turns all white. And that means it's turned crystalline and it's not going to work for you anymore. I've investigated nucleating agents as well. But the problem is that you would have to pre-mix these and you'd have to get really good exfoliation. And by exfoliation, I just mean really well mixed. Yeah, homogeneous mixture. And actually, you want to intercalate it. You want to kind of inside the polymer chains really well, interacting with each polymer chain. You want to separate the crystalline areas. And that will decrease the crystalline, well, that will decrease the process, the time to the crystals form. All right, so I kind of talked about this a second ago. There's been more people that have performed additive manufacturing with filaments than there have been FGF. There's been a couple of papers I've seen published, and they are kind of going through each parameter, and each parameter is important, but the two main important temperatures are the bed and the extrusion temperature and the rate that you're printing at. The slowest you can, the best. And even so slow, it may make you become impatient. About 20 millimeters per second or so. It's pretty slow. But you can control the crystalline like that and you can get really good prints. And you want to have an enclosure. I put a little heated fan in there. I'm kind of debating not having that in there just because of the airflow. I don't know how many people have taken chemistry class here, but if you have a solution of a solid that you're trying to recrystallize and you have any sort of agitation of that liquid, each time you agitate that, it forms a little nucleation and you'll see solid just crash out at the bottom of your solution and you have to redo it because you don't have good crystals. And so it's a similar thing to what we're doing here. So any sort of air, any sort of movement of your print surface, that'll cause it to crystallize really fast. And also, when you're extruding the first layer, you want it really close to the bed, but after that, immediately after that, you need to raise it up because you don't want it to touch the molten layer below that because that's just agitating it. And that's that's essentially doubling up the amount of extrusion you have, because now the flow is doubling because you're going back and forth over the same molten polymer that already has been extruded, and it won't be successful. So now we'll go into some of our current study. We're working with quite a bit of partners. Our primary partner, or not primary, but one that we work with very closely, is Habitat for Humanity here in Austin. They have a restore, and they have waste that they usually have and get rid of, either to a dump but usually it ends up going into some sort of waste pile. And but they have to pay money for that. And so we're working with them to basically allow them to go ahead and take that waste and print from it. So we help them with that. Let's see. That should have been a little ahead of that. So I took this from your PowerPoint, Samantha. But our vision is to for a future where communities can lead change as self-sustaining builders of circular economy. And our mission is to, as with ReCreateIt, is to turn plastic into valuable products using cutting-edge 3D printing technologies with community-led design. We're committed to crafting zero waste future with championing sustainability and creating jobs that empower and uplift communities. Okay, so I immediately jump into some of our prints, but this is just one of them. This is just one color. But we go to the restore. I should probably skip forward because I don't have. Sorry, guys. So every month, me and Chris go to the restore, and we go through all their waste, and we have right here the survey of what we get. And so you can see that polypropylene is the highest amount of material that we get. And so we focus most of our work on that. But all the other polymers that we were picking up are pretty much polyolefins as well, except for the polyethylene terephthalate right there. But so we've really focused on that. And so they have a lot of polymer that they can print with, and we've had a lot of polymer to play with to practice. So this right here is a print. This has got polyethylene and polypropylene in it. I took some cap that came from a vial that we maybe put a solvent in or something, and granulated that up, and then mixed that with clear polypropylene from a laundry basket. My mission is to create a stool or something functional of that sort and large. But I always have this curve up right here. So it's still, no matter how much I practice with it, that's a very challenging thing to do, mainly because these corners, that corners where the stress concentrates, it makes it really challenging to print that. So a lot of our prints, you'll see that are successful, have a rounded bottom. If I want, I have this little miniature kind of granulator. It's more like like a rice, like you chop a type of cornmeal or something, but it's really high RPM, and I just chop up these little things in it. But you can also use that to mix your polymers up. And so even if you can imagine taking a bunch of waste from a bunch of different sources. They could be different ages, they could be different molecular weights, they could be contaminated of some sort. And so the best thing you could do is to mix them up 100%, even just blending, so that your print is consistent throughout. The last thing you want to have happen is clog up your nozzle, and then just because you didn't mix it up well, because it has some high molecular weight in there of some sort. These are some of Chris's prints. He does really good. We've been mixing different colors in. You can get laundry baskets, trash cans, paint cans, anything, and mix them up. But that's kind of where we're at right now. We talked about the restore some. We're providing them with a Gigabot. We're providing them with a Gigalab, granulator, dryer, and with the technology or the skills to go ahead and print their own. So me and Chris are training them on how to do this work themselves. Sorry, I have how to do this work themselves. And pretty confident that they can do that. We'll start with some of the rounded objects, and then Chris and I are also still working on getting up to some more complicated parts. And I think in a few minutes you'll see some of those. But yeah, this is the work. So we go in there, and I didn't finish. I don't know how I didn't finish that. But we go in there, we sort the plastics that she has in the waste, and then we clean them. We print with them. We practice printing with them. But we go through a granulator first, and that's set up at the restore as well. So everything we need to do is there, and now we just need to train them. So that's kind of where we're at right now. This is an example of the Gigalab. Well, they'll have their printer in there. They'll have a workstation. I don't know if they'll be able to fit all these desks in there, but they'll have their dryer in there. They'll have a granulator in there. So everything that they could need to have a fully functional lab is set up, and then they can sell those parts that they make. That's me, the Gigalab delivery. I forgot to mention before this ends that we're working with UT as well. So they have a set of designs and a design tool. And so the user can go through this design tool and pick the part that they want, and they could change it. So if, say, they want one of those faces, they could change the the angle at which it's turning. So you can have wider or sharper curves around there. You can have different colors. You can, and we're also working with stools still. We're doing functional decor. And so Chris, for example, he makes scoops and things like that for his printing, but we've done planters. I did a Buddha head, things like that. And I thought I had some pictures in here of that. Well, I guess not, but so yeah, so we've gotten way more complicated than just stools and just the vases, but this is still the hardest thing to do. So that's kind of where we're at, and I think that was too fast, Samantha, but that's where I'm at. Thank you for coming.
Thanks for that really interesting presentation, Amber. I know it's been a lot of work, so it's fun to be able to share it with the community.
Yeah.
Does anybody have any questions for Amber? This part will be recorded, and then we can turn off the recording if anyone has any additional questions.
I noticed you were using the little like pads on all the corners. I'm assuming the biggest challenge you're facing is adhesion to the bed, as opposed to like interlayer adhesion, or oh no.
No. So what I find the most challenging now, because I've got the adhesion down. If you do the very, very low, the right bed temperature, and you have build-tech polypropylene is the best. That stuff, it'll keep it from curling up, but what will happen is you'll have the layer, like, so you have your part, right? You have your part, and right there, the crease where it's touching the bed from your mouse ears or whatever you're using, that's where it'll crack, not the adhesion. So it breaks that layer first, but it's not cracking that much as you go up. Now, if you add a bunch of colors in, it kind of does. So you kind of have to be careful. You really want to mix it up, but it makes it less pretty. So we're kind of working with that.
Right. Oh, interesting. So because as you have a less homogeneous mix, then you're getting cracking at all those sites. But then also,
yeah, you can see it kind of as it changes colors, it'll crack a lot right there.
Right. But then at that first to second layer interface. Interesting.
Yeah, really that first one is just because it's so good. Even after that happens, it'll start to curl a little bit, but the rest of the part is still on there so good that you have to rip it off. You almost break the part sometimes to get it up. So it's a really good adhesive. You kind of if you have it too hot, I feel like it sticks too good. So you kind of got to play with that temperature too. But Magic is also good. The polypropylene with the glass filling, so the GF, that's also good.
So is that happening at that kind of first layer because it's essentially transitioning to the out of the melt state?
I feel like it's because that's the weakest point. Right?
Okay,
It's
that makes sense.
Thinnest layer, the rest of it's. So what happens as you stack the layers on top of each other, the inner layer should not be really a problem if you have done it right, because they go through a co-crystallization process. So that makes the bond way stronger than you can even imagine. So if you were to take one of those little blocks, even the curled ones like that, and do it in like a tensile adhesion test, you would see that it would maybe not even break. So that's not a problem. It's really just that little weak spot right there, and this at the corner. Yeah. So it finds like I was saying, how those corners of the print itself have the highest amount of stress buildup. Same thing.
Right, totally. It concentrates it all. That makes sense.
Yeah.
Awesome. Thanks.
That's a great question, Adam. Does anyone else have any questions for Amber?
Hi, Amber. This is Kelly Bradley at Lamar University. And we're still kind of getting up to speed with our Gigabot, but we've been trying to do some systematic studies. And we've actually been looking at both the print speed and the extrusion rate, trying to sort of optimize those. Have you looked into that at all, like the extrusion rate? And do you have any suggestions?
So I think me and Chris might differ on this one. He uses an extrusion factor like at 1.05 or something. I don't use that. I feel like it every time I increase the extrusion factor, I feel like it agitates the polymer too much. Does that make sense? I don't know if that makes sense, but I think of them as people, and so I don't want it touching the surface. And when I increase that, I feel like it's pushing more into the surface. I feel like you can get that flow optimized another way.
Yeah, we've probably been looking kind of the other way of slowing the extrusion down. The problem we've actually haven't really branched out beyond the PET-G that we were given by you guys, but a problem that we see is that a lot of times it collapses on us. And so the thinking was that there was just, it was extruding too quickly. There was just too much heat, and it just,
Are you talking about polypropylene?
No, we're planning on looking at polyethylene, but we haven't quite got there yet. We're still working with PET-G at this point.
PET-G, I've worked less with that. I just know if it's not dry, that's a problem. I don't know if you're drying it really well, but I do know for polypropylene, it does really good. Even at fast speeds, you're risking the layer lift up eventually with it too fast. But it does go, and it does really good overhangs too. It's crazy material. It's really good stuff. Yeah. Polyethylene, I've done some of that. It's just the temperature is so high. It can be a challenge. You may need to have a nozzle heater.
I don't think we have one, so we'll have to get in touch with you for that. It may be a little while yet before we graduate on the PET-G though. But thank you, Amber.
Yeah.
Does anyone else have a question? Well, we'll go ahead and turn the recording off, and if anyone wants to ask a question within this group. Michael, let us